My name is Michio Kaku, and today I would like to explore one of the most intriguing and mysterious phenomena in modern science, UFOs, or as they are officially termed today, unidentified aerial phenomena, UAPs. For decades, these mysterious sightings have fascinated the public, sparked debate in scientific circles, and prompted governments to investigate in ways that were once unimaginable. As a theoretical physicist, my goal is to examine this phenomenon not through the lens of sensationalism, but through careful, evidence-based reasoning. I aim to provide a scientific perspective, grounded in physics, while acknowledging that there are aspects of these sightings that remain genuinely unexplained and worthy of rigorous study. Throughout this lecture, we will explore the history of UFO sightings, examine modern reports and official investigations, analyze these events through the principles of physics, and consider their implications for humanity's understanding of our place in the cosmos. We will also reflect on the philosophical and ethical questions that arise when confronting the unknown, all while maintaining a neutral, analytical perspective rooted in observation and evidence. To begin, let me outline the structure of our discussion today. First, I will examine the historical context of UFO sightings, from early reports in ancient and modern times to the well-known cases that shaped public perception in the 20th century. Second, we will move to the modern era of UAP investigation, including military encounters, radar tracking, and the notable Pentagon reports that brought renewed legitimacy to the field. Third, we will analyze the physical constraints and possible explanations for these phenomena, considering everything from misidentified natural events to highly advanced experimental technologies. Fourth, we will place these phenomena in the broader context of life in the universe and the challenges of interstellar travel. Finally, we will consider the psychological, social, and ethical dimensions, concluding with reflections on future research and the lessons that these mysterious sightings provide for scientific inquiry and human curiosity. The story of UFOs is as much about human perception in society as it is about mysterious objects in the sky. While the term UFO may evoke images of extraterrestrial spacecraft, it is important to begin with a simple but crucial point. Unidentified does not imply alien. It simply means that, given the data at hand, we cannot currently classify the object using known phenomena or technology. In science, uncertainty is not a weakness, it is a doorway to discovery. History is replete with examples of observations that were initially inexplicable, only to be understood later with better instruments, more refined theory, and rigorous analysis. The same principle applies here. The unknown challenges us to investigate, to develop new tools, and to question our assumptions about reality. In addition to military and government reports, the scientific community occasionally investigated these phenomena. Notable cases include sightings by astronomers and physicists who approached the subject with analytical rigor. For example, radar and optical observations were analyzed in controlled studies to determine whether atmospheric refraction, temperature inversions, or optical illusions could account for the reported motion and behavior of the objects. Often, conventional explanations sufficed, but some cases resisted explanation even after careful study. These anomalies remain valuable, not because they prove extraterrestrial origin, but because they challenge our understanding and motivate the refinement of observational techniques. Historical cases also include encounters by commercial airline pilots, whose testimonies have been considered particularly credible due to their expertise in identifying aircraft, weather phenomena, and celestial objects. Some pilots reported observing luminous objects moving at incredible speeds, performing rapid maneuvers, or maintaining positions impossible for conventional aircraft. In other instances, ground-based radar confirmed anomalies corresponding to pilot reports. These corroborated sightings, spanning multiple continents and decades, form a substantial dataset that has captured the attention of both skeptics and serious investigators. From my perspective as a physicist, these reports represent a fascinating problem, a set of observations that defy immediate explanation, demanding careful scientific attention. Even in the early 20th century, reports of strange aerial phenomena can be traced back to World War II. Pilots described mysterious lights, sometimes called Foo Fighters, following aircraft over the skies of Europe and the Pacific. While initially suspected as secret enemy technology, many of these sightings were never fully explained. They exemplify a recurring pattern: trained observers encountering objects whose characteristics cannot be reconciled with known technology or natural phenomena. These historical threads connect the modern UAP phenomenon with a long continuum of unexplained aerial observations, reinforcing the need for systematic, scientific investigation rather than dismissal. The early history of UFOs demonstrates several key points that remain relevant today. First, the phenomenon has persisted across decades, continents, and technological eras, suggesting that it is not merely a product of mass hysteria or isolated misperceptions. Second, multiple independent observers, including highly trained personnel, have reported credible and consistent accounts. Third, while many sightings can be explained by natural or human-made phenomena, a small percentage remain genuinely unexplained, forming the basis for continued investigation. Together, these insights establish a framework for understanding UAPs, not as fringe speculation, but as a legitimate subject for scientific inquiry. As we transition from the historical context of UFO sightings, we arrive at the modern era, a period in which the phenomenon has been taken seriously not only by the public, but also by governments and defense organizations. For decades, UFOs were relegated to the realm of anecdotal reports, popular culture, and conspiracy theories. However, the release of multiple verified encounters by trained military personnel has transformed the conversation, demanding that the scientific and defense communities analyze these phenomena systematically. Among the most compelling evidence are the reports from U.S. Navy pilots who have encountered objects exhibiting flight characteristics far beyond conventional aircraft. These encounters have been meticulously documented, often involving multiple corroborating sensors, and provide a wealth of data for scientific analysis. One of the most famous modern cases is known as the Tic Tac encounter, which occurred off the coast of California in 2004. In this incident, Navy fighter pilots observed a white, elongated object, approximately 40 feet in length, moving at incredible speed without any visible means of propulsion. The pilots described the object as having no wings, no exhaust, and no discernible control surfaces. What made this encounter particularly intriguing was the object's behavior. It accelerated rapidly, executed sharp turns at extreme angles, and hovered momentarily before disappearing from sight. These maneuvers, if taken at face value, would subject any human pilot or conventional material to immense G-forces, forces that would likely destroy both pilot and vehicle. The incident was simultaneously recorded by infrared cameras and corroborated by radar systems on board ships, creating a multi-sensor dataset that left analysts puzzled. The Tic Tac has become a benchmark case in the study of UAPs, exemplifying the kinds of encounters that defy easy explanation while remaining rigorously documented. Following the Tic Tac encounter, other high-profile Navy incidents received similar attention. Among these are the Gimbal and Go Fast videos, both captured by fighter jets in 2015 and 2019 respectively. The Gimbal video shows a rotating object moving against strong winds, maintaining a stable orientation while performing rapid, precise maneuvers. The Go Fast footage depicts an object skimming over the ocean surface at high velocity, with motion verified by both infrared imaging and radar. In these cases, trained pilots, experts in visual observation and aircraft identification, confirmed that the objects did not resemble any known aircraft, drones, or meteorological phenomena. The consistency of these reports, combined with sensor confirmation, challenges the notion that all sightings are misperceptions or illusions. Here we encounter a subset of UAPs that remains genuinely unexplained, warranting careful scientific attention. The significance of these encounters was amplified in 2020 when the U.S. Department of Defense officially released the videos to the public, confirming their authenticity. For the first time, government acknowledgement transformed what had been dismissed as fringe speculation into a legitimate topic for study. Subsequently, congressional briefings and official reports recognized that some UAPs remain unidentified even after thorough investigation. Importantly, the language used in these reports is neutral and analytical, focusing on the need for further observation and study rather than drawing sensational conclusions. This shift marks a crucial turning point. UFOs are no longer merely a topic of speculation, but an active subject of inquiry, analyzed with the tools of modern science and defense technology. From a scientific perspective, these modern encounters raise profound questions. How can an object accelerate rapidly without visible propulsion? How can it hover, change direction abruptly, and achieve high velocities while seemingly defying the limitations imposed by aerodynamics and human engineering? One possible explanation is that some of these phenomena represent advanced, classified human technology. Governments around the world invest in highly secretive aerospace programs, which may employ experimental propulsion systems, autonomous guidance, and stealth capabilities. Historically, technologies such as the U-2 and SR-71 aircraft were considered impossible by civilian observers until their existence was revealed. Modern hypersonic vehicles and drone technologies continue this trend, potentially explaining a portion of contemporary UAP encounters. In this scenario, the unknown objects are not extraterrestrial, but rather the product of human ingenuity operating under the veil of secrecy. However, a smaller subset of encounters resists these explanations. Multi-sensor confirmation, precise radar tracking, and pilot observation collectively present phenomena that cannot be readily reconciled with known technology. In the Tic Tac case, for example, the lack of observable propulsion, extreme maneuverability, and absence of sonic booms present a combination of characteristics that challenge current aerospace engineering. If these observations are accurate, they suggest either a fundamentally new approach to propulsion and flight, or an error in interpretation due to instrumentation or perspective. Here, the role of physics becomes critical. Any explanation must obey the fundamental laws of nature, including conservation of energy and the limitations imposed by mass and inertia. While speculative physics concepts, such as gravity manipulation or inertial damping, may offer hypothetical solutions, these remain untested and purely theoretical at present. It is also worth noting the international dimension of modern UAP observations. While the U.S. Navy cases are among the most documented, reports from other nations, including Japan, Russia, and the United Kingdom, describe similar phenomena. For instance, in Japan, commercial airline pilots have reported objects moving at unusual speeds over major flight corridors. Russian military pilots have described high-velocity aerial anomalies performing maneuvers inconsistent with their aircraft capabilities. Even in Europe, radar operators have occasionally detected unexplained aerial targets, prompting investigations. The convergence of reports from multiple countries and independent observers suggests that these phenomena are not confined to a single region or culture, reinforcing the need for global scientific investigation. An important aspect of modern UAP analysis is the integration of multiple observational modalities. High-resolution radar, infrared imaging, optical cameras, and pilot testimony provide complementary perspectives, reducing the likelihood that anomalies are purely perceptual or sensor errors. For example, when radar confirms the trajectory of an object observed visually and an infrared camera captures its thermal signature, the probability of coincidence decreases significantly. This methodological rigor exemplifies the scientific approach. Corroborate observations across independent instruments and maintain a cautious, analytical mindset. Even when conclusions remain uncertain, this approach ensures that the study of UAPs aligns with established scientific standards.
The Pentagon era also introduced the notion of UAPs as potential national security concerns. Unknown aerial objects, regardless of origin, could pose risks to airspace integrity, surveillance systems, and defense operations. This practical dimension adds urgency to the scientific study, as understanding the nature, capabilities, and origins of these phenomena is essential for both safety and technological preparedness. From my perspective, this intersection of science and policy highlights the broader significance of UAPs. They are not merely curiosities, but potentially impactful events that demand careful, multidisciplinary investigation. In summary, the modern Pentagon era marks a profound transformation in the study of UFOs. High-profile encounters by Navy pilots, corroborated by radar and infrared sensors, have shifted the conversation from speculation to evidence-based inquiry. While many sightings may ultimately be explained by human technology, atmospheric phenomena, or observational errors, a subset remains genuinely unexplained, challenging scientists, engineers, and policymakers alike. These phenomena serve as a catalyst for innovation, prompting the development of advanced observational tools, rigorous analytical methods, and a disciplined approach to understanding the unknown. The convergence of history, technology, and science in these modern cases provides a rich foundation for the next phase of analysis, examining the physical constraints, propulsion possibilities, and scientific implications of these extraordinary sightings. As we examine these modern UAP encounters through the lens of physics, it becomes clear that understanding their behavior requires a careful application of fundamental principles. Physics acts as a referee, separating what is possible from what is impossible, guiding our analysis with immutable laws that govern matter, energy, and motion. Observations from Navy pilots, corroborated by radar and infrared data, suggest that some objects accelerate almost instantaneously, change direction abruptly, and hover without visible means of support. If such behavior is interpreted literally, it would subject conventional aircraft or human occupants to forces beyond structural tolerance. For example, abrupt deceleration from supersonic speeds in a fraction of a second would generate thousands of G-forces, sufficient to destroy any known material or biological tissue. Such considerations demand that we explore alternative explanations while remaining grounded in empirical science. One possibility is that some UAPs represent highly advanced human technology. Modern aerospace engineering is progressing at extraordinary speed. Hypersonic vehicles, capable of Mach 5 or higher, are under active development, along with autonomous drones and adaptive control systems that allow unprecedented maneuverability. Stealth technology and novel materials contribute to capabilities that may appear extraordinary to observers outside specialized programs. Historically, secret aircraft such as the U-2 and SR-71 were initially dismissed by civilian witnesses as anomalous phenomena until their existence was publicly acknowledged decades later. In this context, some modern UAPs may be experimental human-made craft with propulsion, guidance, and materials technology not yet revealed to the public. This explanation accounts for many sightings, particularly those occurring near military test ranges or sensitive airspace.
Yet, there remains a subset of observations that resists explanation through known or classified human technology. These cases, including the tic-tac, gimbal, and go-fast encounters, exhibit a combination of acceleration, sudden changes in direction, and apparent inertial-free motion inconsistent with current aerospace engineering. To explore such behavior scientifically, we turn to the principles of motion, energy, and force. According to Newtonian mechanics, an object in motion must obey the conservation of momentum, and any change in velocity generates corresponding inertial forces. If an observed UAP truly moves with negligible inertia, it implies either a novel manipulation of fundamental forces or a misinterpretation of the observational data. This distinction is critical. Science requires us to consider both the limitations of human perception and instrumentation, as well as the potential for genuinely novel phenomena. Speculative physics provides conceptual frameworks for considering how such extraordinary motion might occur without violating fundamental laws. For instance, some theories propose the manipulation of gravity or inertia through exotic energy fields. Concepts like inertial dampers, gravity shielding, or warp field propulsion exist in theoretical physics literature, though they remain untested in practice. These ideas are not wild fantasies. Rather, they are consistent with the known laws of physics under specific, highly speculative conditions. A craft capable of locally modifying gravitational interaction could, in principle, reduce inertial effects, allowing extreme acceleration without destructive g-forces. Similarly, electromagnetic propulsion concepts could, hypothetically, provide thrust without conventional exhaust. While we do not have experimental evidence for these mechanisms at scale, considering them helps frame the problem scientifically. We ask not whether the phenomena violate physics, but whether they challenge our current engineering capabilities and understanding. Another critical factor is the environment in which UAPs are observed. Many incidents occur at high altitudes, near the ocean, or in areas with complex atmospheric conditions. Temperature inversions, reflections, and radar anomalies can all affect the perception and measurement of motion. Infrared imaging may be influenced by thermal gradients, while optical sensors can be distorted by lighting conditions or lens artifacts. Even trained pilots may misinterpret rapid motion when relying on limited visual cues. In analyzing UAPs, it is therefore essential to apply rigorous cross-validation using multiple sensors, as was done in the Pentagon-confirmed incidents. Multi-instrument corroboration reduces the likelihood that apparent impossible motion is purely perceptual or instrumental, allowing scientists to focus on phenomena that genuinely defy conventional explanation. Energy requirements also impose significant constraints. Accelerating a massive object to high velocity in a short time requires vast amounts of energy. In conventional terms, a 40-foot object performing extreme maneuvers would need energy levels far beyond current aircraft engines. This consideration strengthens the possibility that some UAPs involve either unknown physics or extremely advanced propulsion technology. From a scientific perspective, we must remain skeptical but open-minded. Extraordinary claims require extraordinary evidence, but we also recognize that limitations in current technology do not preclude future breakthroughs. The history of physics and engineering is filled with examples where seemingly impossible feats became feasible once new principles or materials were discovered. The study of these phenomena also benefits from statistical and analytical approaches. By compiling and categorizing sightings, we can identify patterns, correlations, and outliers. For instance, many UAP encounters occur near naval training zones. suggesting that human technology or testing may account for some observations. Conversely, sightings in remote regions, confirmed by multiple independent instruments, may point to anomalies worthy of deeper study. Rigorous data analysis allows scientists to separate routine, explainable events from those that demand closer investigation. In this way, statistical methods become a critical tool in the scientific study of UAPs, ensuring that conclusions are evidence-based rather than speculative. It is also instructive to consider the relationship between observed phenomena and the speed of light. Physics imposes an absolute limit. No object with mass can travel faster than light in a vacuum. Any observation suggesting otherwise must be interpreted with caution. In many cases, apparent instantaneous motion may result from perspective effects, limited sampling rates, or sensor latency. By applying careful analysis, we can estimate realistic velocities and acceleration profiles, refining our understanding of what is physically plausible. This approach demonstrates the importance of combining observational data with theoretical constraints, a hallmark of scientific rigor. Finally, the physics of UAPs intersects with broader questions about the potential for extraterrestrial intelligence. If we consider the possibility that some objects might represent technology from advanced civilizations, we must confront the immense challenges of interstellar travel. The distances between stars are staggering. Even the closest star system is over 4 light-years away. Achieving such travel would require propulsion systems and energy management far beyond our current capabilities, as well as solutions for sustaining life or structural integrity over prolonged journeys. While this possibility remains highly speculative, it underscores a central principle. Any proposed explanation must be consistent with the laws of physics, whether the origin is human, natural, or otherwise. In conclusion, analyzing UAPs through the lens of physics provides both constraints and insights. Some phenomena can be explained by misperception, environmental factors, or classified human technology. Others remain genuinely anomalous, challenging our understanding of motion, energy, and propulsion. By applying rigorous analysis, multi-sensor verification, and theoretical frameworks, we can investigate these phenomena scientifically while maintaining skepticism and intellectual honesty. This approach exemplifies the balance that must guide our study: curiosity tempered by discipline, imagination guided by evidence, and a commitment to understanding the unknown through the principles that have always governed the universe. As we continue our investigation into UFOs and UAPs, it is crucial to consider these phenomena in the broader context of the universe and the search for life beyond Earth. The universe is vast, ancient, and filled with billions of stars, each potentially hosting planetary systems. Modern astronomy has revealed thousands of exoplanets, with a significant number lying within the so-called habitable zone, where temperatures allow for liquid water, a fundamental ingredient for life as we know it. These discoveries suggest that planets capable of supporting life may be far more common than previously imagined, and statistically, the emergence of life elsewhere in the cosmos is not only possible, but perhaps likely. Yet probability does not guarantee presence. The emergence of intelligent life capable of technological development, communication, or interstellar travel is a separate and far more complex question.
The search for life has progressed dramatically with the advent of advanced telescopes, such as the Kepler Space Telescope and the James Webb Space Telescope. These instruments allow scientists to analyze planetary atmospheres, searching for biosignatures such as oxygen, methane, or water vapor. Each discovery of a potentially habitable exoplanet adds to the probability that life exists beyond our planet.
The famous Drake equation attempts to quantify the number of civilizations in the galaxy capable of communication, incorporating factors such as the rate of star formation, the fraction of stars with planets, and the likelihood of life developing intelligence. While many of these variables remain uncertain, the equation provides a useful framework for thinking systematically about extraterrestrial life and the probability that advanced civilizations might exist somewhere among the stars. However, even if intelligent civilizations exist, the distances involved in interstellar travel are immense. Our nearest stellar neighbor, Proxima Centauri, is over 4 light-years away, a distance equivalent to roughly 25 trillion miles. With current spacecraft, it would take tens of thousands of years to traverse this distance. The laws of physics, particularly Einstein's theory of relativity, dictate that nothing with mass can travel faster than light, placing a hard limit on travel times. Consequently, any civilization attempting to reach Earth from another star system would require technology far beyond our current engineering capabilities. This includes propulsion systems capable of sustaining high velocities, shielding to protect against cosmic radiation and collisions with interstellar particles, and solutions for energy management and life support over prolonged journeys. Given these constraints, the hypothesis that UFOs are spacecraft from extraterrestrial civilizations becomes increasingly challenging to support. It is not impossible in principle, but the technological barriers are formidable. An advanced civilization capable of overcoming these obstacles would likely have mastery over energy, propulsion, and materials science at levels orders of magnitude beyond our own. They might harness exotic energy sources, manipulate gravitational fields, or employ methods of communication and travel that we cannot yet conceive. While this remains speculative, it provides a valuable framework for understanding why some observed UAPs appear so extraordinary. They may be glimpses of phenomena that challenge the limits of current human technology and understanding. The implications of this cosmic perspective extend to the way we interpret modern sightings. Many UAP encounters occur near populated regions, military zones, or coastal areas, which might suggest human technological activity rather than interstellar origin. However, the rare unexplained cases invite consideration of the broader context. If life and intelligence are abundant in the galaxy, it is at least statistically plausible that some observations could represent advanced non-human technology. Even if we cannot confirm this today, the mere possibility encourages rigorous observation and systematic documentation. In this sense, the study of UAPs becomes intertwined with the larger quest to understand our place in the universe and the prevalence of life beyond our planet. The question of interstellar travel also highlights the importance of understanding the physical limitations of any potential craft. Acceleration, energy requirements, and relativistic effects impose strict constraints. For example, reaching a significant fraction of light speed would require energy levels currently inconceivable, as well as mechanisms to protect the craft and its occupants from interstellar dust traveling at relativistic speeds. Even hypothetical methods such as warp drives, while theoretically permissible under certain solutions to Einstein's equations, remain purely speculative and far beyond practical implementation. These considerations reinforce the need for careful, physics-based analysis of any reported UAP behavior. Extraordinary motion must be reconciled with the laws of nature. Another fascinating consideration is the possibility that some UAPs might employ technologies that exploit principles of physics we have yet to master. For example, manipulation of gravitational or inertial fields could theoretically allow rapid acceleration and abrupt directional changes without the destructive forces associated with conventional flight.
Similarly, energy fields capable of reducing friction or generating thrust without exhaust could enable behaviors that appear impossible under current engineering paradigms. While such technologies remain theoretical, they provide a scientifically grounded way to conceptualize how observed UAPs might operate within the framework of known physics, rather than defying it entirely. This cosmic perspective also emphasizes the importance of observation and verification. If advanced civilizations exist, they may employ detection avoidance strategies, operate on scales beyond our perception, or utilize communication methods we cannot yet decode. Similarly, Earth-based UAPs may exhibit behaviors that challenge sensor systems or human observation. Consequently, continued monitoring with advanced multi-sensor systems, including radar, optical, and infrared instruments, is essential. The integration of artificial intelligence and machine learning for anomaly detection and pattern analysis further enhances our ability to distinguish genuine anomalies from misinterpretations or mundane phenomena. Finally, contemplating UFOs in the context of life in the universe encourages reflection on the philosophical dimensions of scientific inquiry. These phenomena confront us with uncertainty, challenge our assumptions, and invite humility. The universe is far larger and more complex than any single human civilization can comprehend, and our current technology represents only a fraction of what may be possible. In this context, the study of UAPs is not merely about identifying objects in the sky. It is about training ourselves to observe carefully, think critically, and remain open to possibilities that extend beyond our immediate understanding. The interplay between skepticism, curiosity, and imagination exemplifies the scientific method at its best, pushing the boundaries of knowledge while adhering to the rigorous standards of evidence and reasoning. In conclusion, the cosmic perspective on UFOs and UAPs emphasizes both probability and constraint. Life may be abundant in the galaxy, but interstellar travel imposes formidable challenges. Observed phenomena may represent human technology, natural events, perceptual errors, or in rare cases, phenomena that challenge our current scientific understanding. By situating UAPs within the broader search for life and exploration of the universe, we gain a more comprehensive framework for investigation, one that integrates physics, astronomy, engineering, and critical analysis. This approach allows us to remain open-minded without abandoning scientific rigor, ensuring that our exploration of these mysterious phenomena advances knowledge rather than speculation.
As we broaden our examination of UAPs, it is essential to consider not only the physical and technological dimensions, but also the psychological, perceptual, and socio-cultural factors that shape how these phenomena are observed and interpreted. Humans are, by nature, pattern-seeking creatures. Our brains are exquisitely tuned to detect regularities, recognize motion, and interpret sensory input in ways that help us survive in a complex environment. However, this remarkable ability also introduces vulnerabilities: the tendency to perceive meaningful patterns where none exist, the influence of prior expectations, and the effects of cultural framing. When observing lights in the sky or anomalous movements, even trained pilots and observers can be influenced by these cognitive biases, which may amplify or distort perception. Recognizing these human factors is not a dismissal of the phenomena, but an essential part of a comprehensive scientific analysis. Socio-cultural influences also play a pivotal role. The modern concept of UFOs has been shaped extensively by media, literature, and cinema. Since the mid-20th century, countless books, television programs, and films have depicted extraterrestrial visitors and advanced spacecraft, embedding a set of cultural expectations into the collective consciousness. These narratives can subtly shape both eyewitness reports and public interpretation. For example, Witnesses may unconsciously describe unusual lights as structured vehicles or as behaving with intelligence, influenced by popular depictions. This effect is compounded by social reinforcement. Communities fascinated by UFOs provide validation, discussion, and shared frameworks for interpreting experiences. From a scientific standpoint, these socio-cultural influences must be carefully accounted for when analyzing anecdotal reports or unverified sightings. Despite these psychological and cultural dimensions, there remains a subset of UAP encounters that cannot be explained by perceptual error or social influence alone. Multi-instrument verification, radar, infrared, and optical sensors, combined with reports from trained observers, provides robust evidence that some phenomena are genuinely anomalous. The existence of such unexplained cases underscores the importance of maintaining an analytical balance, skepticism tempered by openness to possibilities consistent with empirical data. Science thrives on anomalies, for it is precisely the unexpected, the unexplained that often leads to new insights, technologies, and understanding. The broader implications of UAPs extend into areas of public policy and ethics. Governments have historically maintained secrecy surrounding aerial phenomena, often citing national security concerns. While some secrecy is understandable, excessive concealment can hinder scientific inquiry, limit public understanding, and erode trust. Ethical considerations demand transparency, especially when unexplained phenomena could have implications for safety, airspace integrity, or international security. Sharing verified data responsibly allows the scientific community to participate in analysis, provides a check against unfounded speculation, and encourages international collaboration. In this sense, the study of UAPs intersects with broader questions about the ethics of knowledge dissemination and responsible governance. Moreover, UAPs serve as a catalyst for technological innovation. Investigating phenomena that challenge conventional engineering can drive research in sensor design, materials science, propulsion, and computational analysis. For example, developing multi-sensor platforms capable of capturing high-speed, high-altitude anomalies pushes instrumentation to its limits. Similarly, using artificial intelligence and machine learning to identify, categorize, and analyze anomalous behavior enhances our capabilities in data processing and pattern recognition. In this way, even unexplained phenomena have tangible benefits. They inspire innovation, drive scientific progress, and cultivate skills that may have applications far beyond the study of UAPs themselves.
Philosophically, the study of UFOs challenges humanity to confront uncertainty and embrace curiosity. These phenomena remind us that knowledge is provisional and that the universe is more complex than our current models can fully capture. They encourage intellectual humility and acknowledgement that despite centuries of scientific achievement, there remain questions that resist easy answers. Engaging with such mysteries cultivates a mindset essential to scientific discovery, the balance between skepticism, imagination, and rigorous evidence-based analysis. This philosophical stance is vital not only for the study of UAPs, but for science as a whole, promoting a culture of inquiry that embraces challenges and anomalies rather than dismissing them out of hand. Socially, UAPs also serve to unite communities of curiosity. Across cultures and generations, interest in aerial phenomena has inspired dialogue, debate, and collaborative investigation. Citizen scientists, amateur astronomers, and professional researchers alike contribute observations, document anomalies, and develop analytical tools. This grassroots engagement complements formal scientific and governmental research, expanding the observational network and enriching the dataset. In an era where data from satellites, drones, and high-resolution cameras is increasingly available, participatory science can play a crucial role in refining our understanding of these phenomena and in fostering public engagement with scientific methodology. The ethical dimension extends to interpretation and communication. Responsible analysis requires transparency regarding uncertainty, acknowledging what is known, what is unknown, and what remains speculative. Exaggeration, sensationalism, or the premature assertion of extraterrestrial origin undermines scientific credibility and public trust. Conversely, careful, evidence-based explanation, including the acknowledgement of observational limitations, demonstrates intellectual honesty and provides a model for critical thinking. In this regard, the study of UAPs becomes an exercise not only in observation, but in scientific communication, illustrating the principles of evidence-based reasoning, analytical rigor, and public accountability. Finally, reflecting on the intersection of psychology, culture, technology, and ethics reveals a holistic picture. UAPs are not merely objects in the sky. They are phenomena that engage the full spectrum of human inquiry. They challenge our understanding of physics, engineering, and the natural world. They stimulate innovation and cross-disciplinary research. They invite reflection on human perception, cognition, and social influence, and they highlight the ethical responsibilities inherent in both governance and scientific practice. In this sense, the study of UFOs transcends simple categorization. It becomes a lens through which we can examine the interplay between human curiosity, technological advancement, and the persistent mysteries of the universe. In conclusion, the psychological, socio-cultural, and ethical dimensions of UAPs remind us that observation is never purely mechanical. Human perception, cognition, and culture shape what we see, interpret, and believe. At the same time, multi-sensor verification and rigorous scientific methodology provide a counterbalance, ensuring that anomalies are scrutinized with evidence-based rigor. By integrating these perspectives, we gain a more comprehensive understanding of UAPs, one that respects both the human observer and the objective data, that considers cultural context while adhering to scientific principles, and that maintains openness to discovery while upholding analytical discipline. This integrated approach exemplifies the modern, rigorous study of UFOs and underscores why this field, far from being a fringe speculation, represents a legitimate and exciting area of scientific inquiry.
As we draw together the threads of this lecture, it is important to reflect on what the study of UFOs, or UAPs, teaches us about the scientific process, human curiosity, and the nature of the unknown. Across decades of observation, from historical sightings to modern Pentagon-confirmed encounters, we encounter a spectrum of phenomena. Many explained, a smaller subset partially understood, and a fraction genuinely anomalous. These anomalies, resistant to current explanation, are not failures of science. They are invitations to expand our instruments, refine our theories, and deepen our understanding of the physical universe. Science thrives on precisely this type of challenge: the unexpected, the unexplained, and the extraordinary. It is in confronting these phenomena with disciplined inquiry that knowledge progresses and our perspective on reality evolves. The first lesson is one of humility. Despite centuries of technological and scientific advancement, we remain limited by our tools, our understanding, and our observational reach. The universe, in all its complexity, offers phenomena that do not neatly conform to our expectations or models. The tic-tac, gimbal, and go-fast encounters exemplify this challenge.
behaviors seemingly impossible within the context of conventional physics and engineering, yet rigorously documented. Whether these objects represent advanced human technology, natural anomalies, or, in the most speculative scenario, extraterrestrial intelligence, they confront us with the limits of current knowledge. Humility in science is not weakness, but strength. It encourages continuous observation, rigorous testing, and openness to new possibilities. The second lesson involves the importance of multidisciplinary analysis. UAPs cannot be understood solely through one lens. Physics provides constraints and theoretical frameworks, while aerospace engineering contextualizes maneuverability and propulsion. Psychology and cognitive science help interpret observer perception, while sociology and cultural studies explain how societal narratives influence reports. Ethics guides the dissemination of information, ensuring transparency without compromising safety or security. Only by integrating these domains can we construct a coherent, scientifically valid understanding of UAPs. This holistic approach exemplifies the complexity and richness of modern scientific inquiry. It is rarely isolated, often requires collaboration, and is enriched by perspectives from diverse fields. Third, we learn the value of technological innovation driven by mystery. The observation of anomalous aerial phenomena has historically catalyzed advances in instrumentation, data analysis, and aerospace engineering. Radar systems are refined to detect and track high-speed objects. Infrared sensors capture precise thermal signatures, and optical instruments achieve unprecedented resolution. Artificial intelligence and machine learning enhance pattern recognition and anomaly detection. Even when the phenomena themselves remain unexplained, the process of observation and analysis accelerates scientific and technological progress. In this sense, the pursuit of understanding UAPs benefits society regardless of the ultimate origin of the objects. It strengthens observation, engineering, and analytical capacity while cultivating expertise for future scientific challenges.
The fourth lesson lies in the rigorous application of physics and critical reasoning. Some might be tempted to interpret unexplained phenomena as evidence of alien visitation. As a physicist, I must caution against premature conclusions. Extraordinary claims require extraordinary evidence. Observations must be reconciled with the laws of motion, energy, and relativity. Anomalous acceleration, abrupt directional changes, and apparent inertia-free motion are analyzed not only for what they suggest about potential technology, but also for how they fit within the known laws of nature. This careful approach preserves scientific integrity, distinguishing speculation from evidence-based interpretation. By maintaining this standard, we ensure that the study of UAPs remains a credible, serious domain of scientific inquiry. Looking to the future, several directions are particularly promising. First, continued deployment of multi-sensor observation networks will enhance the reliability and quantity of data. By combining radar, infrared, optical, and satellite-based monitoring, scientists can reduce uncertainty and corroborate independent observations. Second, the use of artificial intelligence and big data analysis allows rapid processing of vast observational datasets, identifying patterns that might otherwise remain hidden. Third, international collaboration opens opportunities for cross-validation, reducing biases associated with national or cultural perspectives and enabling shared scientific methodology on a global scale. These strategies collectively represent the next frontier in the scientific study of UAPs, ensuring that inquiry proceeds systematically, transparently, and rigorously. The future also requires attention to public communication and education. Transparency in reporting, clear explanation of uncertainties, and careful contextualization of evidence are essential. Miscommunication, sensationalism, or premature speculation can undermine public trust and hinder scientific progress. By presenting findings clearly and responsibly, the scientific community can engage the public, inspire young scientists, and cultivate a culture of curiosity and critical thinking. UAPs thus serve as a unique educational opportunity. They stimulate interest in science, physics, engineering, and observation, bridging popular fascination with rigorous methodology. In this way, unexplained aerial phenomena contribute to society, not only through direct scientific insight, but also through the inspiration they provide for future generations of researchers. Philosophically, the study of UAPs challenges our understanding of the universe and our place within it. Whether the ultimate explanation is terrestrial, extraterrestrial, or natural, these phenomena remind us of the limits of human perception and knowledge. They encourage exploration not only of outer space, but of the fundamental principles governing reality. The universe is a laboratory filled with anomalies, contradictions, and surprises. Engaging with these mysteries cultivates intellectual humility, curiosity, and resilience, qualities that are as essential to scientists as are empirical methods and analytical rigor. In this sense, UAPs exemplify the spirit of discovery, reinforcing the idea that the pursuit of knowledge is as important as the knowledge itself. In conclusion, the study of UAPs embodies multiple dimensions of human inquiry: historical, technological, scientific, psychological, ethical, and philosophical. From early sightings by civilians and pilots to the modern Pentagon-confirmed incidents, these phenomena have challenged observers to reconcile evidence with expectation. Physics and engineering provide constraints, psychology and sociology provide context, and ethics guide responsible dissemination and analysis. By maintaining a commitment to evidence, rigor, and intellectual honesty, we ensure that the investigation of UAPs contributes meaningfully to science, technology, and human understanding. These lessons extend beyond the specific phenomenon. They illustrate the broader process of inquiry, the value of curiosity, and the importance of disciplined, open-minded observation. As we look ahead, the journey of exploration continues. Future research leveraging advanced sensors, AI-assisted analysis, and international collaboration promises to deepen our understanding of these enigmatic objects. Every unexplained sighting, every anomaly that challenges our instruments represents an opportunity to refine our methods, expand our knowledge, and confront the limits of what is known. Whether the objects are advanced human technology, natural phenomena, or something beyond our current understanding, they embody the enduring human desire to explore, to question, and to comprehend. In this pursuit, science, curiosity, and the relentless drive to understand converge, offering not only answers, but a framework for facing the unknown with courage, rigor, and imagination. To further appreciate the complexity and scope of UAPs, it is important to examine a series of historical and global case studies. These accounts, spanning multiple continents and decades, illustrate the persistence and diversity of sightings, reinforcing the notion that the phenomenon is not isolated or culturally constrained. While many cases have been explained by natural or human-made factors, a substantial subset remains unexplained, demanding careful documentation and analysis. In this section, I will detail some of the most notable encounters, highlighting their characteristics, observational evidence, and the analytical challenges they present. One of the earliest documented sightings occurred in 1897 in the American Midwest during the so-called airship wave. Across states such as Kansas, Nebraska, and Missouri, citizens reported mysterious cigar-shaped craft moving silently across the sky. These craft were described as having propellers or rudimentary wings, sometimes accompanied by humanoid operators visible through portholes. While contemporary analysis suggests possible misidentification of weather balloons, astronomical objects, or hoaxes, the sheer number of independent reports across widely separated towns indicates a mass observation phenomenon that captivated the public imagination. The airship wave serves as an early example of how anomalous aerial phenomena can capture collective attention, stimulate investigation, and challenge conventional explanations. In Europe, similar sightings have been recorded throughout the 20th century. During World War II, pilots reported the Foo Fighters, glowing orbs or lights that appeared to follow aircraft over both European and Pacific theaters. Initially, these were suspected to be secret enemy weapons, yet no corresponding technological program accounted for their behavior. Observers consistently described the lights as intelligent in motion, performing rapid maneuvers and maintaining formation around aircraft. These sightings exemplify a recurrent pattern. Highly trained observers, often under stressful conditions, encountering unexplained aerial objects exhibiting unusual flight characteristics. While wartime stress and environmental conditions may have contributed to perception anomalies, the consistency and repeatability of these accounts suggest that at least some observations corresponded to real, unidentified phenomena.
Moving forward to the post-war era, the 1952 Washington, D.C. sightings remain particularly compelling. Over a series of nights in July, radar operators at Washington National Airport detected multiple objects moving across the city skyline. Simultaneously, visual observations were reported by both civilian and military personnel. The objects performed erratic, high-speed maneuvers that defied conventional aircraft capabilities. Despite attempts to track and intercept these objects using fighter jets, none could be engaged. The U.S. Air Force conducted formal investigations, including Project Blue Book, and concluded that while many sightings were explainable, a small number remained unidentified. The Washington sightings exemplify a convergence of visual and radar evidence, illustrating the challenge of interpreting reliable data when objects behave in ways inconsistent with contemporary technology. In South America, Argentina and Brazil have produced numerous compelling reports. For instance, in 1986, multiple witnesses in Colares, Brazil, reported luminous objects that appeared to descend near inhabited areas, emitting beams of light that allegedly caused burns and physiological effects. Military personnel and local authorities investigated, documenting physical traces such as scorch marks on trees and soil. While some explanations include atmospheric phenomena or hoaxes, the documented physical evidence and consistency of eyewitness testimony highlight the importance of careful multidisciplinary study. These cases underscore the potential for UAP encounters to leave tangible traces, expanding the domain of investigation from purely observational reports to measurable physical effects. In Japan, commercial pilots have reported anomalies over flight corridors, describing objects moving at speeds exceeding known aircraft capabilities and performing abrupt maneuvers. One notable case in 1986 involved multiple airline crews and ground radar operators detecting objects performing synchronized motion with precision difficult to attribute to instrumentation error. Japanese authorities conducted internal investigations, acknowledging the phenomena as unexplained aerial objects, though results were not widely disseminated at the time.
Such international cases demonstrate that UAP encounters are not culturally or geographically isolated, supporting the notion of a global phenomenon that merits systematic scientific study. Russia has its own extensive history of UAP reports, both civilian and military. In the 1980s and 1990s, Soviet Air Force pilots reported encounters with objects capable of rapid acceleration, sudden changes in direction, and hovering without visible propulsion. Some accounts include radar verification and photographic evidence, though access to full documentation remains limited due to classification. These sightings, similar to their Western counterparts, reveal that highly trained observers frequently encounter objects defying known technological capabilities. By comparing global reports, common patterns emerge: luminous or solid objects, extreme maneuverability, sensor corroboration, and resistance to conventional explanation. These shared characteristics provide a foundation for scientific investigation, suggesting that the phenomenon transcends local misperception, isolated hoaxes, or specific technological development.
Notable European cases include the Belgian UFO wave of 1989-1990, involving triangular-shaped craft observed over multiple nights by thousands of citizens, confirmed by military radar. Witnesses described massive, silent triangles with lights along the edges, moving slowly yet performing rapid, precise maneuvers. Pilots and radar operators independently verified these sightings, producing some of the most compelling multi-source data in the UFO literature. Official Belgian military investigations concluded that a portion of the sightings remained unexplained, emphasizing that the phenomenon is not merely anecdotal or folkloric. From a scientific perspective, such multi-source verification provides a rare and valuable dataset, allowing detailed analysis of motion, size, shape, and luminosity, and offering opportunities to explore physical explanations, whether human-made, natural, or otherwise. Additionally, the case of the Rendlesham Forest incident in the United Kingdom, December 1980, provides an intriguing example of sustained multi-witness observation. U.S. Air Force personnel stationed in England reported a series of luminous phenomena over multiple nights, including observations of strange lights in the forest, unexplained markings on the ground, and radar anomalies. Witnesses described metallic craft with unknown propulsion characteristics, and some reported interactions suggesting intelligent control. While skeptics have offered interpretations such as misidentified lights or hoaxes, the consistency of multiple independent observations across time and instrumentation makes the case compelling. It illustrates the complex interplay between human observation, environmental conditions, and unexplained phenomena, highlighting the need for careful documentation and rigorous analysis. From these historical and global cases, several important patterns emerge. First, highly trained observers consistently report anomalous objects that defy immediate explanation. Second, multi-sensor corroboration, including radar, optical, and infrared evidence, strengthens the credibility of observations. Third, the phenomena often exhibit characteristics inconsistent with known aircraft, natural phenomena, or conventional physics, though interpretation must remain cautious and evidence-based. Finally, UAPs appear across diverse geographic regions, cultures, and historical periods, suggesting a persistent phenomenon that cannot be attributed solely to local factors, folklore, or mass hysteria. Taken together, these global case studies underscore the need for continued, disciplined scientific investigation. Observations must be systematically documented, cross-verified using multiple modalities, and analyzed within the framework of known physical laws.
While speculation about origin, terrestrial, extraterrestrial, or natural is inevitable, the primary focus must remain on careful observation, measurement, and analysis. By studying these historical and contemporary cases side by side, patterns, anomalies, and trends emerge, guiding future research and helping prioritize observations that merit the most rigorous scrutiny. As we examine the modern landscape of UAP research, it becomes essential to consider the role of government documentation, official reports, and scientific assessments in shaping both public understanding and the analytical approach. Over the past 2 decades, governments around the world have shifted from dismissing UFOs outright to acknowledging their legitimacy as phenomena worthy of structured investigation. In the United States, this transformation is exemplified by the release of several Pentagon-confirmed UAP reports, congressional briefings, and the establishment of formal investigative programs designed to catalog and analyze unexplained aerial objects. One of the most significant developments occurred in 2017, when the Department of Defense officially confirmed the existence of multiple UAP videos captured by Navy pilots. Among these, the Tic Tac, Gimbal, and Go Fast videos have become emblematic of the Pentagon-era approach. They provide high-resolution visual and infrared evidence, corroborated by radar tracking, and involve observations from trained, highly credible personnel. The release of these videos to the public marked a profound departure from decades of secrecy and speculation, signaling that the phenomenon was not merely anecdotal or a matter of folklore, but required rigorous scientific and policy attention. Importantly, these reports emphasized caution. The data confirmed the presence of unexplained objects, but did not jump to conclusions about origin, preserving scientific neutrality. In 2020, the Pentagon established the Unidentified Aerial Phenomena Task Force, UAPTF, to centralize the collection, analysis, and reporting of UAP incidents. The task force aggregated hundreds of encounters, categorizing them according to observables such as shape, flight characteristics, and sensor corroboration. A key insight from these reports is that the majority of UAPs observed can be explained as balloons, drones, atmospheric phenomena, or optical illusions. However, a significant minority remain unexplained even after exhaustive investigation. These unexplained cases share common features: extreme acceleration, lack of visible propulsion, the ability to hover, rapid directional changes, and multi-sensor confirmation. Such characteristics are difficult to reconcile with known human technology and warrant continued observation. Congressional interest further amplified the scrutiny of UAPs. In 2021, a formal report to the United States Congress summarized 144 UAP encounters, highlighting that only 1/3 could be explained through conventional means. The remaining 2/3 were classified as unexplained, emphasizing the necessity for scientific inquiry rather than speculation. Importantly, the report refrained from attributing extraterrestrial origin, instead framing the phenomena as potential risks to national security and aviation safety. This neutral, evidence-based approach exemplifies the balance that must guide the study of UAPs: recognition of unexplained anomalies without presuming their nature or origin, preserving analytical rigor while acknowledging uncertainty. Internationally, similar initiatives reflect a growing recognition of the phenomenon. The United Kingdom's Ministry of Defense conducted systematic investigations under Project Condign, analyzing sightings and radar data over decades. While the report concluded that most cases were conventional in nature, a small subset remained unexplained. Other countries, including France, Brazil, and Japan, maintain ongoing programs to study unexplained aerial phenomena, often collaborating with civilian scientists and academic institutions. These efforts demonstrate that the study of UAPs is not confined to one nation or political system, but represents a global endeavor, requiring transparent reporting, multidisciplinary analysis, and careful consideration of scientific and security implications. Scientific organizations have also weighed in on the study of UAPs. In 2021, the National Aeronautics and Space Administration, NASA, announced the formation of an independent study team to examine UAPs from a strictly scientific perspective. Their mandate includes evaluating existing data, identifying gaps, recommending observation strategies, and establishing protocols for future measurement. The involvement of NASA marks a critical step: the application of rigorous scientific methodology to a topic historically relegated to anecdote, speculation, or popular culture. By employing standardized instruments, cross-verified observations, and hypothesis-driven analysis, the scientific community can distinguish genuine anomalies from misperception, sensor error, or conventional technology. A central theme of these government and scientific efforts is methodological rigor. Multi-sensor verification remains paramount. Radar confirmation, infrared imaging, optical observation, and pilot testimony collectively increase the reliability of data. Statistical analysis and anomaly categorization enable researchers to identify recurring patterns, distinguish outliers, and prioritize cases for deeper study. Importantly, transparency and documentation are critical. Providing open access to sanitized data fosters public trust, encourages independent verification, and facilitates international collaboration. In this sense, UAP research exemplifies the principles of modern science applied to phenomena that challenge conventional understanding: rigorous observation, systematic analysis, and cautious interpretation. Ethical considerations underpin these investigative efforts. Governments must balance transparency with national security, ensuring that sensitive technology or operational capabilities are protected while still providing sufficient data for scientific scrutiny. Miscommunication or sensationalism can erode public trust, encourage misinformation, and complicate the analytical process. By contrast, careful, responsible reporting of verified phenomena fosters a culture of intellectual honesty, encouraging both public engagement and scholarly inquiry. In this respect, UAP studies illustrate the intersection of science, policy, and ethics, demonstrating how rigorous methodology and responsible communication mutually reinforce credibility and progress. Beyond immediate safety and policy concerns, the analysis of government and scientific reports also has implications for broader scientific research. These reports often highlight gaps in observational capacity, sensor coverage, and data integration, identifying areas where technological development is needed. Advanced multimodal sensing platforms, high-resolution imaging, and AI-assisted anomaly detection are increasingly viewed as essential tools. The presence of unexplained phenomena in well-instrumented environments underscores the importance of improving observational infrastructure, which benefits not only UAP research, but also broader aerospace, atmospheric, and astronomical science. In summary, modern government reports and scientific assessments reflect a dramatic shift in approach, from secrecy and dismissal to transparency, systematic documentation, and evidence-based analysis. The Pentagon's UAPTF, congressional reporting, NASA's scientific study, and international programs collectively illustrate that UAPs are now recognized as legitimate subjects of inquiry. Importantly, these reports maintain a careful balance, acknowledging unexplained phenomena without asserting origin, emphasizing methodological rigor, and fostering international and interdisciplinary collaboration. This approach embodies the scientific principles of observation, measurement, and hypothesis-driven analysis, applied to one of the most persistent and intriguing mysteries of our time. By integrating historical cases, modern Pentagon confirmations, and international scientific assessments, we gain a comprehensive framework for understanding UAPs. The global multi-temporal perspective highlights recurring patterns, identifies the subset of genuinely anomalous phenomena, and informs strategies for future observation and research. In this context, UAPs are not merely curiosities or cultural artifacts. They are challenges to our understanding of physics, technology, and perception, demanding a systematic, disciplined, and transparent approach. Through careful analysis, rigorous methodology, and ethical responsibility, we can continue to explore these phenomena while maintaining the standards of science that have consistently expanded human knowledge throughout history. As we advance further into the modern scientific approach to UAPs, it is essential to consider the evolving landscape of observational technologies, data analysis methods, and research frameworks designed to rigorously document and interpret these phenomena. In the past, UAP reports relied heavily on anecdotal testimony, often from civilian observers, occasionally supplemented by photographic evidence of limited quality. While these reports were valuable in stimulating initial investigation, their reliability was constrained by the limitations of human perception, environmental conditions, and the quality of early instrumentation. Today, however, scientific and governmental initiatives have transformed UAP research into a multidisciplinary, technology-driven field capable of capturing high-fidelity data and performing robust analysis. High-resolution optical systems represent one of the most significant advances in observation technology. Modern cameras, capable of ultra-high-definition imaging, coupled with advanced stabilization and low light sensitivity, allow researchers to capture visual evidence with unprecedented clarity. Paired with multispectral capabilities, these instruments can record phenomena across visible, infrared, and ultraviolet wavelengths, revealing details that were previously inaccessible. Infrared imaging, in particular, provides insights into thermal signatures, allowing analysts to distinguish between conventional aircraft, atmospheric phenomena, and anomalous objects exhibiting unusual heat patterns. The integration of optical and infrared data enables cross-verification, reducing uncertainty and enhancing the credibility of observational records. Radar systems remain a cornerstone of UAP detection and tracking. Modern radar networks, including ground-based and airborne platforms, provide real-time data on object speed, trajectory, altitude, and maneuverability. Multi-static radar configurations, where multiple sensors triangulate the position of an object, improve precision and reduce the likelihood of misinterpretation caused by reflections or interference. Additionally, synthetic aperture radar technology enables high-resolution imaging even under adverse weather conditions, providing further insights into object structure and movement. When radar data is cross-referenced with optical and infrared recordings, a multi-sensor verification approach emerges, ensuring that observations are reliable and reducing the influence of perceptual or instrumental errors. Beyond traditional sensing technologies, the integration of artificial intelligence has revolutionized UAP analysis. Machine learning algorithms can rapidly process vast quantities of observational data, identifying patterns, anomalies, and correlations that would be impossible for humans to detect manually. AI systems can classify objects based on shape, flight characteristics, and sensor signatures, distinguishing conventional aircraft, drones, weather phenomena, and potentially anomalous objects. By continuously refining models with new data, these systems improve predictive accuracy, enabling researchers to prioritize the most intriguing or unexplained cases for further study. The combination of AI, high-fidelity sensors, and multispectral imaging represents a paradigm shift, allowing the scientific community to approach UAPs with rigor, speed, and precision previously unattainable. Proposed research programs emphasize both technological enhancement and methodological rigor. Comprehensive observational networks, strategically distributed across global locations, aim to maximize coverage and reduce blind spots. Each network incorporates redundant sensors, optical, infrared, radar, and potentially acoustic, ensuring cross-verification and multimodal analysis. Additionally, data integration platforms collect, store, and process observational data in real time, enabling rapid analysis and long-term trend identification. By combining these technologies, researchers can create a continuous high-resolution record of aerial phenomena, facilitating pattern recognition, anomaly detection, and systematic study.
Simulation and modeling play an equally important role. Advanced computational techniques allow scientists to recreate observed phenomena within controlled virtual environments, testing hypotheses about motion, propulsion, and environmental interaction. For example, objects exhibiting rapid acceleration or abrupt directional changes can be modeled using both conventional aerodynamics and speculative physical frameworks, such as gravitational manipulation or exotic energy fields. By simulating these scenarios, researchers can explore the boundaries of plausibility, distinguishing what is physically possible from observational artifacts or misinterpretation. Such modeling also informs the design of future observational programs, highlighting the capabilities needed to resolve remaining uncertainties. Collaboration between civilian and governmental organizations further enhances the scientific rigor of UAP research. Open access platforms encourage citizen scientists and academic researchers to contribute observational data, while government agencies provide infrastructure, funding, and methodological oversight. This cooperative approach ensures that a diverse range of expertise, experience, and analytical tools is applied, increasing the likelihood of meaningful insights. In parallel, international collaboration fosters data sharing, standardization of observational protocols, and cross-validation, reducing the impact of local biases and creating a truly global research framework. Ethical and operational considerations underpin these technological and methodological advancements. Transparency in reporting, responsible data handling, and respect for privacy and security are paramount. While high-resolution imaging and AI analysis enhance observation, they also create ethical responsibilities regarding the dissemination and interpretation of findings. Misrepresentation or sensationalism can erode public trust and compromise scientific credibility. Therefore, all observational programs incorporate clear protocols for verification, peer review, and cautious interpretation, ensuring that conclusions are evidence-based and responsibly communicated. Looking ahead, the integration of emerging technologies promises to further transform UAP research. Quantum sensors capable of detecting minute variations in electromagnetic or gravitational fields could reveal subtle interactions associated with anomalous objects. Autonomous aerial and orbital platforms may provide continuous observation without human intervention, reducing bias and increasing temporal coverage. Data fusion techniques, combining real-time environmental data with high-resolution observation, will allow researchers to contextualize sightings with unprecedented detail. The convergence of these technologies represents a future in which UAPs can be studied with the same rigor applied to other complex natural phenomena, such as hurricanes, seismic events, or astronomical transients. Finally, the pursuit of technological and methodological excellence reinforces the scientific and societal value of UAP research. By rigorously documenting, analyzing, and contextualizing unexplained phenomena, we cultivate a culture of curiosity, critical thinking, and disciplined inquiry.
These efforts advance knowledge not only about anomalous aerial objects, but also about human perception, sensor technology, data analysis, and interdisciplinary collaboration. In this sense, the study of UAPs exemplifies a holistic scientific enterprise. It challenges our understanding, drives innovation, and fosters a systematic, evidence-based approach to exploring the unknown.
As we reach the conclusion of our exploration into UAPs, it is essential to synthesize the insights gained from decades of observation, historical and modern reports, technological advancements, and scientific inquiry. The study of UAPs embodies the convergence of multiple disciplines: physics, aerospace engineering, psychology, sociology, ethics, and data science. By examining these phenomena through a comprehensive lens, we not only attempt to identify the nature of the objects themselves, but also gain profound insights into the processes of scientific observation, critical thinking, and human curiosity. One of the most compelling takeaways is the enduring mystery of unexplained cases. While many sightings are attributable to human-made aircraft, atmospheric events, or perceptual errors, a subset resists conventional explanation. These anomalies challenge our understanding of aerodynamics, propulsion, and sensor interpretation. Some objects display acceleration, deceleration, and maneuverability that would require energy and material capabilities far beyond known human technology. Whether these phenomena are manifestations of advanced terrestrial technology, natural events not yet understood, or indications of intelligent extraterrestrial life, they push the boundaries of human comprehension and invite systematic scientific exploration. The pursuit of understanding UAPs encourages technological innovation at multiple levels. Observation networks employing multispectral imaging, radar, infrared, and AI-driven analysis are refining our capacity to capture and interpret complex phenomena. Computational simulations allow us to test hypotheses about motion, energy requirements, and environmental interaction, providing insight into the physical constraints these objects might overcome. Additionally, collaborative international research programs expand both the volume and diversity of data, ensuring that insights are not limited by national, cultural, or methodological biases. In essence, the search for understanding UAPs accelerates progress across scientific and technological domains, regardless of the ultimate origin of the phenomena. A particularly fascinating area of potential discovery lies in propulsion and energy systems. Some observed behaviors, such as rapid acceleration without apparent exhaust or sudden directional changes without deceleration forces, suggest that our current models of physics may not fully account for the mechanisms at work. While these observations do not immediately imply a violation of fundamental laws, they hint at potential advancements in material science, energy generation, and gravitational or inertial manipulation. Even if such technologies exist only in theoretical frameworks, studying anomalous phenomena inspires scientists to explore possibilities previously considered science fiction. The history of human innovation is replete with examples where observation of the natural world catalyzed breakthroughs in technology, from the flight of birds inspiring early aeronautics to cosmic observations guiding satellite engineering. UAPs may similarly serve as catalysts for unforeseen advancements in physics and engineering. From a philosophical standpoint, the study of UAPs emphasizes the importance of intellectual humility and curiosity. The universe is vast and filled with phenomena that challenge our understanding. Engaging with unexplained objects in our skies reminds us that science is a process, not a repository of answers. It requires observation, critical analysis, skepticism tempered by openness, and a willingness to revise theories in light of new evidence.
UAPs thus serve as a mirror, reflecting both the limits of human knowledge and the potential for discovery when we embrace uncertainty with rigor and imagination.
Moreover, these phenomena raise profound questions about humanity's place in the cosmos. The discovery of life beyond Earth, intelligent or otherwise, would reshape our understanding of biology, evolution, sociology, and philosophy. Even without definitive evidence of extraterrestrial origin, UAPs compel us to confront the possibility that intelligence in the universe may take forms and possess technologies far beyond our current imagination. This consideration does not diminish our achievements, but rather contextualizes them within the broader cosmic landscape, inspiring a sense of wonder, responsibility, and ambition. The cinematic and dramatic aspect of these investigations is equally compelling. Imagine a pilot tracking an object performing impossible maneuvers against the twilight sky, or a radar operator witnessing rapid acceleration that defies conventional aircraft. The human experience of encountering the unknown, the awe, the uncertainty, the meticulous documentation is itself a testament to the scientific spirit. Capturing these moments through careful observation, detailed reporting, and rigorous analysis transforms raw experience into knowledge. Science, in this context, is both a lens and a narrative, a way of turning wonder into comprehension and mystery into discovery. Finally, as we contemplate the future of UAP research, it is clear that systematic, multidisciplinary, and technologically advanced approaches are essential. Continuous global observation networks, AI-driven anomaly detection, international collaboration, and transparent reporting frameworks will deepen our understanding. Each unexplained case, each anomaly that resists current interpretation is not a failure of science, but an invitation to refine our tools, expand our theoretical frameworks, and explore the boundaries of what is possible. In this sense, UAPs are more than isolated curiosities. They are a catalyst for the expansion of human knowledge, the advancement of technology, and the enrichment of scientific methodology. In conclusion, the study of UAPs, from historical sightings and wartime encounters to modern Pentagon-confirmed phenomena, provides a unique intersection of observation, technology, and curiosity. It challenges our assumptions, stimulates innovation, and invites us to engage with the unknown in a disciplined, systematic, and imaginative manner. As we continue to observe, analyze, and hypothesize, we are reminded that the universe is far more complex, dynamic, and mysterious than we can fully comprehend. Whether future research reveals advanced terrestrial technology, unknown natural phenomena, or the existence of extraterrestrial intelligence, the pursuit itself embodies the essence of science, the relentless quest to understand, explain, and marvel at the wonders of the cosmos. And so, everyone, that was all I hope you learned from what I explained today. What type of topic would you like me to explore next? Mention it in the comments and subscribe to my channel so that I can continue providing you with knowledge. Understanding the universe is not just a pursuit of answers, it is a journey of discovery, curiosity, and wonder that propels humanity forward. Let us continue this journey together, always questioning, always exploring, and always striving to expand the horizons of what we know.